Any questions on CPC? Are these things clear, the properties that we got from CPC? All right, very good. So I really invite you to just, later give a very good, deeper look into this construction. And if you see it, we didn't really change the things much, right? We just got, the previous block, and we involve it into the encryption of the next block, and then we just add an initialization vector. But that simple, change has made a significant change, and we just made that, the mode of operation much better. So let's go ahead and talk about a different one, something called cipher feedback, or as short is CFB. And the goal here is that, remember that we said that we would come back and give a better construction for stream ciphers. So now you would see an example that we take in a stream cipher and then a block cipher, and then we turn it into a stream cipher. So this is a very good example of that cipher feedback. So as always, let's start with our definition. For example, over here, we suppose that our MI are no longer 128-bit. We assume that they are S bits. So, let's say S is much smaller than N, equal to N. And let's suppose S is, for example, 8 bits, right? So it's 1 byte or 1 character. So the question is that, is there a way that we can still use AES, but we would be able to turn the AES, which is a block cipher, into a stream cipher, so that we can start to encrypt S bit or 8 bit in this example? And the answer to that is yes, we can do that. So this is the answer. So the idea is that in the beginning, we come up with some initialization vector. And of course, we said that we would choose that randomly. And then I'm going to denote that as IV. So we have made some changes over here. And these changes are a little bit significant. We won't encrypt the message anymore. We already chop our messages, and every of these messages are not 128-bit anymore. They are simply S bits, which is maybe 8 bits. But what we would start to encrypt is the IV itself. So we come up with a randomized, initialization vector. As the first block, we would encrypt this IV with the key itself, and then we get the corresponding, ciphertext. And we always assume that, we would, these blocks are n bit, right? So 128 bit. Let's just define it as a variable to be n bits. So once we get the output over here, we would do one thing. We would take the top S significant bits right over here, and then we would get rid of the rest. We don't need the other ones. Why did we get the top S bits? Because our message to be encrypted is also S bits. So we have produced enough random bits to encrypt the message, and we just XOR it, and then we will compute the corresponding ciphertext C1. And again, for encrypting the next piece of message, we would do a little bit of adjustment. So we know that our C1 now is S bits, right? Or we just talk about 8 bits. What we would do is that we would start to do a left shift. So we would basically do S bits shift to the left. So some of the bits on the top of this V, we would get rid of them. If that is the part, I draw it correctly. And then we want to add the C1 as the initial S bits. So together, this is again n bits or 128 bits, and which can be encrypted by AES. And again, once we get the resulting ciphertext over here, we get rid of the n-s bits, and then we just take the S significant bits. We take that one, we encrypt it with M2, and that would create us this ciphertext to the second piece of ciphertext, and so on and so forth. So you see the combination of the previous message that the previous ciphertext has effect on encrypting the next message. So that chaining effect, you see that here. But there is a significant change, and instead of encrypting the message itself, we are encrypting the initial vector. And after every round, you see that we are keep shifting more bits. So at some point, we get rid of this initialization vector, and everything would be the ciphertext, right? And we would keep encrypting them and plug in the key, and this is the way the algorithm works. So a nice property that we get here is that we don't have to wait for our message M to be exactly 128 bits. It can be much less than that, S bits or 8 bits. So we kind of turn our block cipher into a stream cipher. Remember the one-time pad that we said that we would use that one-time pad idea in future with many different combinations. And we said one way was to use the pseudo-random bit generator. So this is exactly the same idea of pseudo-random bit generator. We are using AES to just generate some random bits, and then we use that random bits of AES to encrypt the message directly, XOR it, right? And so on and so forth. So even though the same idea of one-time pad is somehow applied here, so you see that we are using AES and the same key to expand, some bits of key by encrypting different values with the same key so that we can produce more random bits. Can somebody tell if this is unconditionally secure? Can we discuss that here, you think? Remember that one-time pad was unconditionally secure, and we say that. Yeah.
But since this one would be like a pseudo random generator, then we would not be unconditionally. We would be computational.
Yeah, computational secure. That is correct. Why do you think this is a pseudo random bit generator with the AES? Why not a true random number bit generator?
Because we are. Oh, the first one might be random, the first initialization vector, but after that we keep shifting and then reusing, which would make it not random. There's a pattern.
Right. Let's see it from different lens. So we said that the AES, or any block cipher that we design, is a practical block cipher, right? It is not the ideal block cipher because the key size has been shrunk down to a subset of all keys, right? So this building block that we are using here, which is AES itself, is not unconditionally secure. It is just computationally secure. Okay, so that means that we are using some pseudo-random number generator. For example, AES here itself is not unconditionally secure. It is just computationally secure. So the most we can achieve is, what AES would offer us. Okay, is that clear?
Yes.
All right. So that being said, let's go check the decryption, how the decryption works. So for the decryption again, we use from top to bottom, and then you could see that. So if you start with the IV, we already transfer that IV along with the ciphertext. So if we start with that, we would encrypt it, get this intermediate output, and then we get the S bits. We XOR it with C1, and that would give us M1. And then we use the same C1 to start to shift the IV so that we can go ahead and do the same computation to get the corresponding messages, right? So, after, some shifts, what you would start to see over here is that this is like, C2, this is C1, and then this is the rest of the bits, right? So the IVs keep changing on the top. Changing IV would make different bits after encrypting. and that would generate us different bits to be used as a key to encrypt the messages. So again, we can confirm that even though M1 and M2 are the same, the corresponding ciphertexts would be different, right? Because again, we are starting with some initialization IV, and then we are keep changing the bits that we are generating for encrypting those different those same messages are different. So therefore, the resulting ciphertext would be again different. So we achieve all we wanted to achieve better than the very first algorithm. I want to draw your attention to the very first one, ECB, that we don't want to do this simple thing because it would have a disadvantage that we would leak a lot of information. We have discussed SCBC, a block cipher that would not have that issue, and on the top, because of the initialization vector, we get some good properties. And then the last, we saw that we can basically produce an algorithm called a stream cipher using the AES, which is a block cipher, and the idea is sort of Werner-Bond time pad when you see in the heart. So let's just be a bit more precise on how encryption works. So in case that you're wondering if you can write it down in a pseudocode. So we have two functions over here. So let me define this one. So in the intermediate results, we get S bits and N minus S bits. So this one, I call this one, suppose there is a function that returns this S bits on the top. We call the most significant bits. And then this one is least significant bits, LSB. Right? And then just N minus S, we would go and return, the least N minus S significant bits from this array. So suppose these are two functions that when we call them, they return this corresponding, pieces, parts of the output. So now we start the encryption algorithm. The encryption algorithm, given the key M and some initialization vector, it would output this corresponding ciphertext, and you see that it will concatenate the initialization vector for the recipient to be able to do the decryption. To make the word easier, we start to use a variable called x1, and we just copy IV into x1 in order to encrypt the i's block of a small block of message. I shouldn't say a small block of message, the corresponding I ciphertext, because we're not block cipher anymore. So what I would do is that I get encrypt the xi, which in the beginning is just IV, encrypted with my AES, and then I get the most significant bit of S, which would return this S bits, and then I XOR it with MI, and then the M1, and I produce MC1. And when I go to M2, I would just increase this I by 1, and things would work correctly. But before we start to go to the to encrypt the second message, what we have to do is that we have to change that IV, right? So let me go back. You see that every time I start with IV encrypted, and we have just produced this one. But before I go ahead, I need to change this IV. So I need to do that shift on IV. So the way that I do that is that I take the less, N minus S least significant bit of Xi, which is over here. And instead of doing shift, it's just doing concatenation. I concatenate CI that I just produced over here. So this would be exactly just what we've discussed over here, right? So we take the N minus S significant bits over here, and it would copy paste them here, and it would take C1 and concatenate it to the end of this, and that would become my next IV, sort of, that I need to encrypt. So you see that I would generate X plus 1 to be the, I produce it as we've just discussed. And now I have X2, which now when I go back to this loop, I can do like encrypting the X2, and then take the most significant bits so that I can XOR it with M2 to produce C2, and then I continue doing this for loop over here so that I can encrypt the entire message itself. All right. So this is how the encryption works, and I think the decryption we don't really have to discuss. It is exactly the same way. But one of the most significant changes that we made here is that we actually turn our block cipher into a stream cipher. This is a very important achievement that we have over here. So because of this, we no longer have to produce the ciphertexts, produce a stream ciphers from scratch. So this is a very good example how we actually turn a block cipher into a stream cipher. It's a good example that we don't need to worry about, working on creating a stream cipher. With this notation, an idea of mode of operation, we can actually take any block cipher that is out there in the market, and we just apply this mode of operation and we turn it into our stream cipher, and we are good with that. So there are two more things that we want to discuss before we let it go. So now we want to see what happens if we have transmission error over here. Suppose that I have a transmission error over here, C1. So some of these bits are, flipped, and the recipient can't detect them. So of course, C1 is affected. So of course, M1 would be affected. So what I can see is that C1 goes here. It also affects the decryption of M2, and it will continue. As you can see that C1 is being pushed shift to left. So eventually, after some blocks, this C1 would get out of this IV, and then none of those encryption would depend on that C1 that is already affected. So until that time, all the messages that I get would be affected by that issue. And how many of them would get affected? So if we are talking about the transmission error in CI, so we said that MI would of course be affected, and then the next ceiling of N divided by S blocks would also get affected. So remember this notation ceiling, if you forgot. So for example, if you have 4.2, the ceiling of that would become just 4. And if you have, for example, 4.9, the ceiling of that just becomes 5. So what happened is that if supposing that S equals, let's just work with some numbers. So suppose S is 8 bits, and then we are talking about AES, and therefore N is equal to 128 bits. So given this, it means that MI would be affected, and then MI plus 1 would also be affected, and then all the way to M ceiling of 128 divided by 8, right, would be affected. And right after that, the M 128 divided by 8 plus 1 would not be affected anymore, right? So anything up to here, maybe MI minus 1 was correct. And just because of that transmission error on CI, we missed this many messages in between. And this algorithm also has self-synchronization effect. So that means that anything after this many blocks would get back to what it used to be before, right? And it wouldn't be affected. So that being said, let's say we define here that S is 8, N is 128 bits, so which means that we are talking about 16 characters, right? 16 characters are affected just because we had some transmission bit error over here. So comparing this, I understand that it looked like many different blocks, but in total, we only, got 16 characters affected, which is just like one block of, it would become 128 bits, which means that if we have that issue, we only miss 128 bits. If we go back and compare this value to the CBC, we would miss 2 blocks, but over here, every block was 128 bits, which we missed 256 bits. So comparing that with this stream cipher, even though it looked like we are missing more messages, but the amount of the bits that we miss and information that we lose is actually equal to half of that of CBC, which is just 128 bits, right? So that is the case that we should consider. Just give me a second, guys. My laptop is trying to die. Okay, we're good now. Okay. So this was the old discussion about the CFP. So before we go through a very interesting slide, let me see if we have any question. Is this algorithm clear? Do you have any questions about this algorithm, CFP? So let's just spend some time here and really understand which one is the best one to choose in different scenarios. So I brought up some specific topics. So I want to discuss this with you and see what are your opinions in different scenarios. So if this is only, the security is your concern, which one of these algorithms you would choose, or which one of them you wouldn't choose? So this is the slide we need some interaction because, the more we discuss, the more clear this concept would appear to be here. So I'm giving you these 3 choices of mode of operation that we just learned now. And the question is that if the only concern is security, which of this mode of operations you would use? Somebody says that won't choose ECB. Yes, we saw that ECP, the picture of the penguin. Always remember that it has some issues when the file has some structure. Somebody says CBC. How about the CFP, the latest algorithm that we saw? Yeah. So let me just put them together. Then the only thing we do not want to choose is ECB. So I think only the security is a concern. Then the CBC and the CFB are, going to be your choice. So we don't want to use ECB. I mean, sadly, now that you have learned about ECB, I mean, it's not sadly, it's a very good news. Sorry. The sad point is that a lot of routers and a lot of operating systems, they still support ECB mode of encryption. For example, if you connect your mobile phone through your home Wi-Fi or home router to get your internet, and there would be some negotiation, and then your phone and the router would negotiate for the algorithm for encryption, the key, and a lot of parameters. And one of the things that they would negotiate for is this mode of operation, because the router knows that you want to send messages that are more than 120 bit long. So at the end, you want to use some mode of operation. So one of the takeaway from today's lecture is that if possible, you want to log into your router, and it has a list of mode of operation that your router is ready to configure itself with some other device. So you want to remove ECB from that list, because now you know that ECB is completely insecure, and you do not want that mode to be selected. On your phone, again, some phones, they have this choice. The operating systems like Android, you can choose, you can configure that. You don't want to negotiate on ECB mode of operations and so on and so forth. So that is very important to remember. Okay. Okay, so now we talk that for security purposes, we choose CBC and CFB. So what if I ask you that our concern is not security, we only talk about the speed. So we want to achieve the, the highest speed. I know that, taking out the security, you would say that it's just transmit the message, don't encrypt it at all. That would be the maximum speed. But imagine we still want to use a mode of operation, but regardless of how secure they are, we want to discuss which one is the best case in terms of parallelism. Okay. Any idea which one do you think is the fastest one? Yeah. So everybody, yeah, right answer. Very good answer. So let's go back and see why for those that maybe are a bit lost here. So in terms of this, the ECB, for the encryption and for the decryption, we can achieve the maximum amount of speed. We can, let's say, because you see that when you want to encrypt a message, the encryption doesn't depend on any other, chain, anything other than the message itself. So if you have, let's say, P amount of cores, then you can achieve, a speed of almost P times faster, right? So you can have every core to work on in, one block of a message in parallel, and then you can do that encryption in parallel. How about the decryption? I think we don't have the decryption circuit over here, but for the decryption, we can look from bottom to up, and we reverse everything. So again, we can achieve maximum amount of throughput because, as you can see, nothing is having a chain effect. We don't have any dependency over here, right? Everything is independent. So if you have again P cores, then you can, do P, you can decrypt P blocks of ciphertext at once. You can achieve almost, not always, do P times the speed up. So now the question is that, okay, how about the CBC or CFB? What do you think about those two? Any opinions?
You mean why they're not parallelized?
Yeah, why they are or if they are. So let's look into them. So let's discuss them together. I think it's a little bit hard to see without seeing the algorithm itself. So let's look into the CBC encryption. So in order for us to encrypt, let's say I'm in the middle, CI. In order for me to encrypt this block of message, I need to achieve the encryption of the previous block, right? So it means that if, for example, I want to encrypt C2, I can't do it unless if I finish the encryption of C1 because I need C1 to be used for encryption of C2, right? So, well, unfortunately, no matter how many cores we have, we can't really do much. We have to go one by one, okay? What about the decryption? So looking into the decryption circuit, now the story is a little bit different. You see that suppose I plan out all the ciphertexts over here, and you see that I can go parallel now because there's no dependency. So I can decrypt this one because I already have C0 and C1. For C2, I need to have encryption the ciphertext of C1, which I already have. So, that is already plugged in. So there's no problem. Now I can do, parallelism for decryption. There's no problem for that. So we had to achieve that security, we have given away, the parallelism that we could do for encryption. But however, we have achieved, at least we can do parallelism on the decryption side. So that is at least one thing to keep in mind, that maybe the sender cannot really enjoy to do parallel computation on encryption, but the recipient can actually enjoy that. So let me give you some scenarios for this to become a bit clear. Suppose that we are using this mode of operation to encrypt the files in the disk. So, let's say you encrypt your files on your operating system, and when your disk in your PC or your Mac, when your Mac is booting up, so it needs to decrypt the files, right? And before it can boot up. So you can see that if you use CBC, the time that you write the file, the encryption would take a little bit of time because you can do it in parallel. But however, when you're booting up your system, because now all the pieces of ciphertext are already out there on your disk, so therefore you can do parallelism for the booting up time. So then you can achieve a pretty fast booting time. So that would be one good point for having a CBC. So how about the CFB? Looking into the CFB again, so you see that dependency. So again, sadly for encryption, we cannot use the parallelism, because to encrypt the message M2, we need to have C1 ready. So we can't do much before we wait for encrypt one piece by one piece. But however, on the decryption side, again, you see that we have almost everything ready, right? So when we have C1, C2, and all those things, I can, pre-create this variables very quickly, and then I can do the decryption in parallel. So again, we can achieve this. So given this, then I can tell that ECB is the fastest one, right? And then for number 2, we have CBC and CFB for only decryption circuit, right? For the decryption part, we can achieve that parallelism. So that is one thing to consider. So now, suppose that we only consider about error propagation. So, sometimes the block CI would get affected with some bits. Some bits would flip. Which one you think has the best, the least error propagation effect, so that we would lose the least amount of information?
I have a question about that. With for the CBC, the 128 that we're taking into account is because we're using the EAS encryption, or because this one always use 128 bits?
No, we said that the key bit over here, we always suppose that they're n bits. So if I go to the yes, yeah. So we always say that these are n bits, right? So the n and for AES, n equals to 128 bits, right? So let me write this one here, that it makes it clear for all of them. So that's why we are talking about this block, right? So you can now, if AES is 128 bits, so you set n to be 128 bits and done. And if in future you have any other block cipher that is, I don't know, 500 bits, then you can just change n to 500 bits.
And in that case, since we would be choosing, thus the amount of blocks and the sizes of blocks we're losing is depending on the encryption algorithm we choose, which means that technically we could end up with a M that's smaller than the S that we choose for the CF.
Right. That is correct.
Is that not possible? Yeah.
Right.
Okay.
Correct. Yeah, but the point is, from we assume that you're using AES for all of them. So from that perspective, now we are seeing how many blocks do we lose. So of course, for example, if you use DES over here, DES is only 56 bits, right? But we know that the DES is completely insecure. You don't want to use it. And then, you know, maybe after some years, AES is insecure. So, you know, that you have to move to 512 bits, for example. So it really depends on that, you know, the underlying encryption algorithm that you use over here. But for now, keep this comparison fair. Let's say we always use AES for all of these three algorithms, okay? So if we want to discuss that over here, so error propagation. So ECB is fantastic, right? If you have error on C1, then what happens is that you only miss M1. It doesn't affect any other bits over here, right? So any other block, I'm sorry. So from that perspective, ECB is very good. So you have any issues in bits over here on C1, that only affects the M1. So that being said, then we go to CBC. So in CBC, we said that if you have any, you know, misinformation on C1 over here, so that of course affected that, you know, M1 block of message. And because we use this one for decrypting the other neighborhood block, we would also affect this M2. So any, you know, missing information in one block would cause us to miss 2 blocks of the message, right? So that is something to remember. So it is twice as much as we lose comparing to the ECB, the first algorithm. So how about the CFB? So on the CFB, we said that if we lose any, you know, anything, we would start to miss, of course, that specific S bits, and then all the way to, you know, 100 to n divided by that S bits, right? So that would be the amount of information that we would miss on all of this, you know, blocks. So going back to that question, so error propagation, the best one is again ECB, right? Because you would just miss one block. Then, you know, from amount of the bit, you know, from the number of the block that we would miss, or, you know, number of the character we would miss, then CBC is better because CBC only would miss 2 blocks. So the CBC 2 blocks. And then the CFB, we said that it would miss, you know, 128, or yeah, let me just go with 128. Let me just be n divided by s, number of you know, small blocks. So if we continue with AES, then if we use AES, then n equals to 128 bits. Then it means that over here we would miss 128 bits. Over here we would miss 256 bits. And over here, if S equals to 8, then we are missing 16 blocks. So let me say bits. So we are missing 16 blocks, and every block is 8-bit. So altogether, we are missing 128 bits, right? So from the amount of the information that we would miss, then ECB and CFB are equal, right? Because in both cases, we would only miss 128 bits. However, on CBC, we are missing 2 blocks. That, supposing we use AES, then that means that we are missing 256 bits. Another way to look into this is that you don't care about how many bits you lose, you care about how many blocks you would miss. So if we look at from that lens, then ECB is the best one because you're missing only 1 block. CFB is the second place because it loses 2 blocks. And then the last one goes to CFB because it misses like 16 blocks or 16 characters. So if that is the case, that no matter how you want to look into this. But I think most of the time, we won't want to see how many blocks we would lose. We are talking about how many bits we are missing, right? So in the end of the day, we are transferring some message, and or the best way to measure or loss is the amount of the bits that we lose. So in that case, then ECB and CFB are equal, even though CFB looks like that is missing more blocks. But remember that the number of the bits in every block in CFB is very small. So adding up them together, then they would just become the same as ECB. So I think it would be the same discussion if we want to have for self-synchronized. So all of these algorithms, they have this property of self-synchronized. So meaning that, after, the block CI is missing or some of the bits are, flipped, all of these algorithms after some time, maybe the next block or maybe after 2 blocks or maybe after, 16 blocks, they can correct themselves. And there will be no problem. So those kind of self-synchronization, I think it doesn't really matter because all of them would achieve that, right? So I think after this slide, I think I brought this up here. I really wanted to have you guys to interact about this question, is that now you kind of learn how do you want to choose a mode of operation. So every time that you have a project in future, you want to discuss what is the best mode of operation you want to have, or at least some of them that you do not want to choose. So again, you can have this sort of discussion, and you can just plan it out for yourself with respect to security, speed, error propagation, and self-synchronization. Which one is the one that you want to choose at the end? So I can tell you that, use, for example, CFB is the best one. It appears in all of them as a good one, except for the speed and parallelization. So, it really depends on the scenario that you're working. If you're sending so much information, maybe encryption is very important. Maybe the speed of encryption. Maybe when you're sending so much information, you don't transfer, so much information. For example, you're talking about the IoT device that just reads a sensor value or some of them and try to encrypt and send them. So it should be fine because IoT device doesn't have, much of processing power. You don't talk about many cores. So even though encryption is slow, it is fine because you have most of the time 1 core for your IoT device. So CFB is a good choice, but and also the good thing is that when the server receives those ciphertexts, then your server can decrypt them very quickly because it is parallelizable, right? So these are some scenarios that you can bring up and discuss for yourself before you finalize your choice. But having this kind of discussion would really help you to understand and at least roll out those mode of operation, for example, ECB, that are completely insecure, that you shouldn't be using them. So these are not the only list of mode of operations. So I just brought 3 of them that after you learn these 3, then I think you're good to go and study the other ones. There are many more out there, counter mode operation, and many more Galois fields and different things. I think you have enough now background to now that you understand 3 of them and you can judge. So if you study the new one, you have enough material to study for yourself and see if those new ones are a better fit for your scenario now. All right, I think we are close to your break time. Well, kind of pass it. So let's get a 10 minutes break and we come back. We are going to discuss, we're going to go to the next chapter.